We continue with Fourier transform. Remember last time we defined what's meant by the Fourier transform. Just to remind you, this was our definition here. We solved two examples, one before this, and this was our second example, e to the minus absolute value of x. We commented on the definition, we said many remarks, some connections with the Fourier series, and now before seeing more examples, I like to talk about the so-called inversion formula. So what is meant by the inversion formula? For example, remember in Laplace, when we talked about Laplace transform, Laplace transform, you have a function, you find the Laplace, you get it's a transform. But then, if you remember, you can go back from the transform to the function. So you have the transform, but this time you go back to the function itself. This was like the inversion form. This was denoted by Laplace inverse, if you remember. So for example, just to remind you, for example, if you find the Laplace of the function 1, it's 1 over s. So what is Laplace inverse of 1 over s? It is 1. This is what's meant by the inversion formula in general. So the inversion formula, it's just from the name, it's like the inverse. You're taking something, then you reverse it to get back to the original. This is what's meant by the inversion formula. So what's the inversion formula for Fourier transform? So given a function that is absolutely integrable. So when we say L1, this new notation, we just mean it's an absolutely integrable function. Why do we care about absolutely integrable functions? Because those functions are the only functions that have Fourier transform. So if you have a function like this, we know that the Fourier transform is given by this integral. Fine. Okay, so what does this definition do? This definition, you have like the function, you apply the Fourier transform, it's denoted this way, you get f hat the Fourier transform. Now what we want to see is the other way. So can we have something going back from the transform to the function itself? In fact, yes. What is it? If the Fourier transform is also absolutely integrable, then the function is equal to the almost the same as the Fourier transform. So it's 1 over root 2 pi f hat of w e to the I wx dw. So I intentionally left this space blank. You will see the reason. You'll see the reason. Okay, so if you look at these two integrals, so if you compare this definition with this definition, they look very, very similar, right? So the only difference, maybe the only difference is this negative here, but the other difference is the d, right? This is dx, this is dw, of course, because this is x, this is w. So in fact, the two definitions or the two formulas are very, very similar, except for just the negative sign. That's it. This is the only difference for us between the two formulas. So this is just f hat of w, sorry. Okay, so what is in this side? What is in this side? In this side, usually we write f of x, but to be accurate, this is f of x plus f of x minus. So if you remember this term here, we saw it when we applied the Fourier series, and we applied what's called the Drishna theorem or the Drishna test. In that theorem, we had some relation between the function and the complex or the real Fourier series. And here, in fact, I like to mention this relation, kind of a comparison that simplifies understanding the whole picture in Fourier series. So what was the Drishna theorem in the Fourier series? It was like this. If you have the Fourier series, whether the complex or the real Fourier series, so it's the sum of e to the cn, e to the I n x and from negative infinity to infinity, that's equal to f of x plus f of x minus over 2. Remember, we applied this before. We mentioned that if you have a value, you substitute it into the Fourier series. Is the output equal to the function? Yes, if the function was continuous. But if the function is not continuous, we get this quotient here. It's the average of the limit from left and the limit from right. So if you look at the two formulas now I want to look at this and compare between them. They are almost identical. On the left, you have exactly the same thing, f of x plus f of x minus over 2. On the right, you have the sum. You have the sum here, because here we had the Fourier series, and the Fourier series is defined on integers. So that's why we have the sum. But now we're talking about the Fourier transform, where the w values are not integer values. They are running over all real numbers. So just imagine that you have a sum over all real numbers. So when I say the sum over all real numbers, we don't mean the integers. So just imagine 1, 1.01, 1.001, and so on. In that case, we kind of we understand the thing as the integral from negative infinity to infinity. And the last comparison is, what about this constant? Why do we have it here in the Fourier transform, but we don't have it in the complex Fourier series? The reason goes back to the definition. When we go back to the definition of the complex Fourier series, the Cn was 1 over 2 pi times the integral. While now in our Fourier transform, the definition has 1 over 2 root 2 pi. This is the difference. That's why when we started this chapter, when we started this section, the Fourier transform, we mentioned that this constant is not a big deal. So sometime you see it 1 over 2 pi, 1 over root 2 pi, but you have to stick with your choice. So if you start your definition with 1 over root 2 pi, then there are some consequences. If you don't use it, there are other consequences. So for example, if in the Fourier transform definition, you use 1 over 2 pi. So if you go back to this definition and you say, okay, I don't like the root 2 pi, I want to use 2 pi, that's fine. In that case, what happens in the inversion formula is that you don't see the 1 over root 2 pi. Okay, so I think this should be this comparison should be clear with the complex Fourier series. Okay, so now this formula here, this is called the inversion formula. So what is the role of the inversion formula? The role is as simple as saying, if you have the Fourier transform, you do this integral, you get back to the function, and that's it. This is the way we look at this inversion formula. Now, you might wonder, in Laplace transform, do we have an inversion formula? Because when we studied differential equation course, where we learned the Laplace transform, we didn't mention anything about the inversion formula. We just used tables or our memory to find the Laplace inverse. In fact, there is an inversion formula for the Laplace transform, but it is a bit advanced for our courses. It uses some complex analysis in the formula. Okay, so this is our inversion formula. Let's see how we apply this formula and what are the benefits of using this formula. I'm going back to the example we did last time. So I'm going back to the function e to the minus absolute value of x. So I'm saying, recall that when f of x is e to the minus absolute x, where we have the Fourier transform equals root 2 over pi 1 plus omega square this way. Okay, this is the Fourier transform. We did it. Now, what is the inversion formula? The inversion formula, so in this example, I just want to explain, so there is no find or evaluate or anything. Just let's apply together the inversion formula. What does it say? It says that f of x plus f of x minus over 2 is equal to this thing. Right? Now in my example, the function e to the minus absolute value of x, if you draw this function, how does it look like? E to the minus absolute value of x, it's something like this. So basically it is a continuous function. If it's a continuous function, then you don't need to write the limits from left and right. It's just the function itself. So the function itself is equal to 1 over root 2 pi, the integral negative infinity to infinity. What is f hat of w? F hat of w is the root 2 over pi 1 plus omega square, right, times e to the wx dw. But what is this? Root 2 gets cancelled and you're left with 1 over pi negative infinity to infinity e to the I wx w square plus 1 dw. This is equal to the e to the minus absolute x. What does it mean? Let's see what this means. For example, if you say, let's substitute x as 0. What does this equation mean? If you substitute it into e to the minus absolute x, you get 1. If you substitute it into the integral, you get 1 over omega squared plus 1 d omega. So basically that means the integral from negative infinity to infinity, 1 over is equal to what? Is equal to pi, right? So basically you are finding some integrals using the inversion formula. This integral is easy, right? So if you go to calculus, this integral is just tan inverse and you can get the pi very easy. But what about if you say, okay, let's try the 1. What does the 1 give you? It gives you, so if you substitute 1 into the left, you get e to the negative 1. You substitute it to the right, you get 1 over pi integral negative infinity to infinity e to the I omega, because x is 1, over omega squared plus 1 d omega. So basically, what you found is that the integral from negative infinity to infinity is pi e to the minus 1. And this is a new integral for us. This integral cannot be solved using any of the calculus techniques you did in calculus. In fact, to solve this integral, we have to do some tricky stuff like the Fourier series, like some techniques that we haven't done in complex analysis. So there are some tricks to do this integral, but there is no way we can do it using the calculus techniques. So but again, this is one advantage of using the inversion formula, that you can compute some integrals that are not easy to compute anywhere else. I like to look at this integral, so we just need to analyze what we are getting in this example, trying to understand the whole thing. So what is this integral? This is the integral from negative infinity to infinity cosine omega. I'm just writing the inversion, the Euler formula, which is e to the I omega is cosine omega plus I sine omega. Right? Now, if you look at this integral here, the sine is an odd function. The omega squared plus 1 is an even function. If you divide an odd by an even function, the result is an odd function, and the integral of an odd function from negative infinity to infinity is just 0. So this is the integral from negative infinity to infinity cosine omega over omega squared d omega. What is that equal to? What is that equal to? This is equal to this, right? But this is here is equal to pi e to the negative 1. Pi e to the negative 1. So this is like a new integral that we cannot compute using any of the calculus techniques. Now we can do it. Yes, now we can do it. Okay, so this is one advantage of using the inversion formula. I like here to mention a little remark that I think some of you have already noticed. Let's look at, if you have a function g, what is g hat of omega? It is 1 over root 2 pi integral from negative infinity to infinity g, you will see why I changed my function just to avoid the coming confusion. So this is g of x e to the minus iwx dx, right? So if I ask you what is g hat of x, so imagine, because we are used to write the Fourier transform in terms of x, but we can write, in terms of w, but we can write it in terms of x. So what is it in terms of x? It's the same thing. It's 1 over root 2 pi, but we just need to change the notations. So instead of having g of x, you can say g of y. I'm going to use g of omega, e to the minus, and the omega x, I want to just to switch them. So this will be the same. So you replace the omega by x, the x by omega, you get basically the same thing, but this will be the omega, right? Okay. On the other hand, if you look at the inversion formula and assume the function is continuous, okay? What is f of x? So again, I'm just copying this inversion formula, but for the left side here, I replace this quantity by f of x, assuming that the function is continuous, okay? Just to simplify the stuff we have. Okay. So this will be equal to 1 over root 2 pi integral from negative infinity to infinity. Again, what is the inversion formula saying? F hat of omega e to the I omega x d omega, right? Look at these two quantities. Compare between them. They are exactly the same, right? What is the only difference? Again, the only difference is the negative sign. So I'm going to look at this as 1 over 2 pi negative infinity to infinity f hat of omega e to the minus I omega negative x d omega. So I just changed it to negative negative, that's it. And now compare between this and this. Just look at the two quantities and ask yourself, what is this integral equal to? From the first formula here, from G formula, what is this quantity? You have a function and you integrate it, e to the minus I w. This is it. You look at this, okay? You have a function, g of w. Now instead of g of w, you have f hat of w. So just imagine f hat of w is just replaced by g of w. You will have exactly the same thing. The only difference, you have x up, you have negative x here. So the thing is, instead of having g hat of x to the left, you will have g hat of negative x, right? But what is g? It is f hat. So basically this is f hat of negative x. But at the same time, so let me just make more space. Okay, so according to this formula again, this is equal to what? This is equal to f hat of negative x, right? So now, what is our conclusion? So our conclusion is that f of x that we started with is equal to f hat of negative x. Very nice. This is a very nice formula. But again, please remember, what is this f of x? This f of x is not f of x. It is f of x plus f of x minus over 2. Remember, all the time when we deal with Fourier series, Fourier analysis, if we write f of x equals the series or the integral, we mean this. Even in text box, in very advanced box, we write f of x, but what's meant is f of x plus f of x minus over 2. That's why in measure theory and real analysis, we usually say f of x equals almost everywhere. Yes, it is almost equal to, except at certain points that we can't talk freely here, but this is the idea. Okay, so my conclusion in this remark is that there is a relation between the function and the double f hat, as you see in this formula. F hat negative x is equal to f of x. Okay. Let's take another example, and in this example, I want to go back to the first integral, to the first example here in Fourier transform. Remember, we had this rectangle, the rectangle 1 over the interval -1, 1, and 0 everywhere else. Now we computed the Fourier transform, and it was this function here. And remember, at this stage, we made all the details about this piecewise function and discontinuities. Then we mentioned that the Fourier transform is always continuous, okay? So I'm going to say again, if you go back to the function, so recall that when f of x is 1, this function we've just seen, then f hat of omega is what we have here is just √2 over pi sine omega over omega. Okay, so we have this, and again we don't need to mention this as if omega is not 0. Now if you look at this f hat of omega, in fact f hat of omega is not absolutely integrable. So what do we mean by is not absolutely integrable? We mean that the integral from -infinity to infinity, absolute value of sine omega over omega d omega, this is infinite. This is a little bit harder than the level of this course, but in real analysis courses, it's well known that this integral is infinity. So basically, what is the meaning? This is the sinc function. So what is the meaning of this integral being infinity? If you draw sine omega over omega, it's something like this. It keeps oscillating about the x-axis. So basically, we're talking about this area. Although these areas are getting smaller and smaller, if you add them, the total area will be infinity in the end. So this is why I'm not going to apply the inversion formula on this function, because when we started the inversion formula, we said f hat has to belong to L1. It must be absolutely integrable in order to apply the inversion formula. But in my case, in this function, I can't apply the inversion formula because the function is not absolutely integrable. I wanted to mention this in case we needed to apply the inversion formula for this function. You can't, okay? However, we will do another trick later to see this integral. Okay. So having done the Fourier transform and the inversion formula, it's time, because if you go back to the history, to the Fourier series, what did we do in Fourier series? We started by defining the Fourier series and its inversion formula. In Fourier series, I can say this is the inversion formula in the Fourier series, just the complex series itself. So in Fourier series, what did we do? We defined the Fourier series. We defined the inversion formula. Then we talked about Parseval's identity. We talked about even and odd functions, right? So the organization of the Fourier transform will be the same. We started the Fourier transform. We talked about the inversion formula. Now it's time to talk about Parseval's identity for the Fourier transform and the odd and even cases. For the odd and even cases, these will open the door for other stuff. So I'm going to do Parseval's identity first. So Parseval's identity, or Plancherel identity, in fact, in Fourier transform. But I wanted to call it Parseval just to map it in your mind with what we've done with the complex or the real Fourier series. So what is the Parseval's identity? So if you have a function in L1, then the integral from -infinity to infinity f of x squared is the integral from -infinity to infinity f hat of omega squared. So what does this say? It tells you that if you integrate the square of the function or the square of the Fourier transform, you're getting the same answer. Why is it called Parseval? Why is it related to Parseval's identity in complex series, for example? If you go back to Parseval's identity in complex Fourier series, what is it? It tells you that 1 over 2 pi, integral from negative pi to pi, the function square is equal to the sum from negative infinity to infinity, the cn's square, right? Again, this 1 over 2 pi, don't care about it because this is a consequence of our definition in the beginning. In the new Parseval identity here, we don't see it because we used 1 over root 2 pi when we talked about the Fourier transform. Okay, but if you look at, so if you forget the 1 over 2 pi and you just look at the integral equal to the sum, again, what is the sum? You're adding all the Fourier coefficients, the cn's, from negative infinity to infinity over the integer values, because the cn is defined when n is an integer value. Now, the f hat of omega is defined when omega is a real number. So imagine you need to write the sum from negative omega from negative infinity to infinity, omega being a real number. Again, our translation for this is go to the integral. So basically this summation here becomes like the continuous version of it is the integral from negative infinity to infinity. So this is called Plancherel Theorem, or Parseval's identity. And in fact, for this to be true, and this is very important, but again, you are engineering students, so I don't like to go deep in analysis and the properties. But to be accurate, for this to be true, f of x must be square integrable. What do you mean by square integrable? If you have a function and you square it, the integral could be infinity. In fact, in that case, this will be infinity, don't worry. But usually when we write this statement, when f is in L1 and in L2, the square integrable. But for this statement, just keep in your mind, this is true even if this side is infinity. So if your integral of the square function is infinity, the integral of the Fourier transform square will be infinity. So this covers the case of real number or infinity. Let's see an example to show you how we apply this result. Let's go back to the rectangular function, which is just this example, and we call it rectangular. It's clear because if you draw it, it looks like a rectangle. For this function, so again, for the function 1, when x is between negative 1 and 1, 0 otherwise, what do we have? We have f hat of omega equals root 2 over pi sine omega over omega. Fine. So if you apply Parseval, or again, this is well known as Plancherel's theorem, what is it? It says that the integral from negative infinity to infinity, the function square, is equal to the integral from negative infinity to infinity, the Fourier transform square. Very nice. But if you look at the function is 0 everywhere except on the interval negative 1, 1. So basically the left integral is just the integral from negative 1 to 1 is equal to negative infinity to infinity. If you square the Fourier transform, you get 2 over pi sine square omega over omega square d omega. Now what's the integral on the left? It's 2. So if you cross multiply, you get the integral from negative infinity to infinity sine square omega over omega square d omega. What is that? It's equal to pi. Very nice. This is really a nice integral because this integral, you cannot do it using any of the calculus techniques. So the only way to do this integral is a tricky method like the Fourier transform, like the Parseval's or the Plancherel theorem. Or we need to go to some topics in complex analysis. So again, this is an example where application of Fourier ideas simplify the computations. So this is this integral. From this, by the way, so we applied Parseval's. This is the application. But I like here to show you from this. First of all, if you look at the integral from negative infinity to infinity, sine square omega over omega square, again, this is equal to pi, that's fine. In fact, what is sine square over omega square? Sine square is an even function. Omega square is an even function. When you divide two even functions, the result is even. So this is basically double the integral from 0 to infinity sine square omega over omega square d omega. That's equal to pi. So the integral, you can say the integral from 0 to infinity sine square omega over omega square is basically pi over 2. This is, again, one consequence of that integral. The other consequence, I like to compute, so let's find together the integral from 0 to infinity sine omega over omega. Okay? So I'm going to find this using this. Okay? So I'm going to use the square version of this integral to find the integral. And please be very careful. This integral is not the square of this. Okay? When you have squares, you can't insert the square into the integral. This is very dangerous. So how do we compute this integral? Let's see. So we know that. So again, this is one of the tricks that I like to show you in this course. We know that the integral from 0 to infinity sine square omega over omega square is equal to pi over 2. We already know it. This is it. Okay. Let's look at the left integral. And please remember, we can't do this integral without, for the level of this course, without the Fourier transform. So the idea, let's try to compute it. So we need to do it by parts. So the u is sine square omega. The dv is w to the negative 2. If you differentiate this, this is 2 sine w cosine w. And this is negative w to the negative 1, right? So if you do integration by parts, this plus minus integral. So basically, let's isolate this. So basically, what is this integral? It is negative sine square omega over omega from 0 to infinity, right? Then plus the integral from 0 to infinity to sine omega cosine omega over omega d omega. That's all equal to pi over 2. And please remember, we mentioned this many times, when we deal with improper integrals like this, from 0 to infinity, this is an improper integral. It is an improper integral because of two reasons. The infinity makes it an improper integral. The 0 also makes it an improper integral, although the function is continuous at 0. It has a removable discontinuity. So basically, when we look at this infinity, we imagine we have a limit. This 0, we have a limit. So what is the limit? Basically, as omega goes to infinity, sine square omega over omega. And what's the limit as omega goes to 0? If you look at the first limit, when omega equals infinity or approaches infinity, the sine square is always between 0 and 1. So if you have something between 0 and 1, you divide it by w, which is infinity. Anything, so we're using squeeze theorem, we used it before, so this will be 0. Minus, if you compute the limit at 0, just apply L'Hopital, you get 0. So basically this is 0 plus the integral from 0 to infinity. This is omega. But what is 2 sine omega cosine omega? What is it? This is just the identity for sine 2 omega. All of this is equal to pi over 2. So we have the integral from 0 to infinity sine 2 omega over omega d omega is equal to pi over 2, right? Now, what do we want to find? What we want to find is the integral sine omega over omega. What we found here is the integral of sine 2 omega. So what I'm going to do now is I'm going to substitute 2 omega as t, for example. So in this substitution, when omega is 0, t is 0. When omega is infinity, t is infinity. And when you replace 2 omega by t, you get sine t over, what is omega? Omega is t over 2. So the 2 goes up. What's the dw? It's dt over 2 equals pi over 2. The 2 gets cancelled, and you are left with this integral. Very nice. So the integral from 0 to infinity for sine t over t is exactly equal to pi over 2. It's very nice that this is a very nice example showing you that although the integral of the squares, sine square over omega square, is pi over 2, we're having the same value for sine t over t, which is the same as sine omega over omega. So this is again a very strong example that you can't deal with the square. You can't say the integral of the square is the square of the integral, okay? So basically this is a very powerful example that the area between the function and the x-axis is equal to the area between the square of the function and the x-axis. So this is again one nice application of Plancherel theorem or Parseval's identity. If we go back to the other example, so I'm going to apply Plancherel or Parseval, but for the function e to the minus absolute value of x. Remember, for this function we just applied the inversion formula. We got some nice results, but what happens if we apply, so in this example I want, so if you look at the function e to the minus absolute x, we already have that f hat of omega equals root 2 over pi 1 over omega square plus 1. Okay, we already have this. Now if you apply Parseval identity or Plancherel, what do you get? You have the integral from negative infinity to infinity, the function square equals the integral from negative infinity to infinity, the Fourier transform square, right? So what is it? So the integral from negative infinity to infinity, I'm writing the right term first, 2 over pi 1 over omega square plus 1 square equals the integral, what is on the left? On the left is e to the minus 2 absolute value of x dx. It's very nice that the left integral is not that easy. To do the left integral, you need to do some trigonometric substitutions. But for the right integral, so now I'm computing this integral, not using trigonometric substitutions, but using the very easy integral on the right. So what is the integral on the right? The integral on the right is double from 0 to infinity e to the minus 2x, which is double e to the minus 2x over minus 2 from 0 to infinity, and in fact this is equal to 1. If you substitute the infinity, you get 0. If you substitute the 0, you get exactly 1. This is a very nice result. So basically what we found is that the integral from negative infinity to infinity 1 over omega square is equal to pi over 2. This is again a nice integral that you can find easily using using Fourier techniques. However, the question is, if I give you this integral, so if you look at these examples, I'm giving you the function and the Fourier transform, then we just apply together those identities to obtain these integrals. But the question is, if I ask you, find this integral, how would you think of the function that gives you this, this integral? This is not an easy problem in general. So in general, if you have some experience with certain examples, you can guess the function. But in general, this is not an easy task at all. So don't worry. If you see an integral and you don't know what function you need to use, don't worry about that. Sometimes we use the Fourier transform tables. I will show you these tables next time, or maybe the time after that, after we finish this stuff. So sometimes if you have the Fourier tables, you can match the integral with one of those functions in the table, and then you can guess what your function is. But this is the idea in general. I hope this makes the inversion formula and Plancherel or Parseval's theorem very clear.